Okay, let us start. Good evening, all. Last class, we clipper circuit using ordinary diode. In that, if the diode is an ideal diode, when anode to cathode voltage VAK is greater than 0, it acts as a short circuit. If VAK is negative or less than 0, it acts as an open circuit. So based on the status of the diode, we can identify all node voltages or output voltage, and we have plotted the output waveform for a corresponding input waveform, and we could plot the transfer characteristics also. Now let us bring our Zener diode into the circuit, and this is the circuit symbol of Zener diode. The upper terminal here is called cathode, lower one is anode. If the diode is forward biased or VAK, anode to cathode voltage is positive, similar to our ordinary diode, it acts as a short circuit between its terminals, that is between anode and cathode. So if you are plotting the VI characteristics of the diode, when it is forward biased, it acts as a short circuit, and there is a current from anode to cathode, IF, and its value will be maximum possible value, and that maximum possible value depends on the circuit parameters, and we will put an up arrow. When VAK is positive, the current is maximum, so we'll have an up arrow here. And if VAK is just positive, just greater than 0 volts, since it acting as a short circuit between anode and cathode, the anode to cathode voltage will be always 0. So the current curve remains in the y-axis, and the forward voltage drop is always 0. In the reverse bias, if this is corresponding to forward biased condition, if it is reverse biased, again similar to our ordinary diode, it acts as an open circuit between anode and cathode, and of course current flowing through the diode IF will be 0, so it will be in the negative x-axis. But our ordinary diode never breaks down in the reverse direction. It's an ideal one. You can vary your reverse voltage up to infinity, minus infinity specifically. Even then, your ideal normal PN diode won't breaks down ideally, whereas your Zener diode will breaks down at some voltage in the negative x-axis. We will call that voltage as VBR, B for breakdown, R for reverse. So reverse breakdown voltage VBR. Once it breaks down, the reverse current is very large. Reverse current can take any value, ideally up to infinity. And you should understand that when the Zener diode breaks down, the current flows from cathode to anode in this direction, I or. So first case was a forward bias condition. Current was maximum voltage across the device was equal to 0. And the second, this is region 1. Second region was the device is in reverse biased mode and before breakdown. So I will write in bracket reverse biased mode before breaks down. Second stage. In that it acts as an open circuit, hence the current is 0. Whereas in the third region, it breaks down and current can take any value, ideally up to infinity, in the reverse direction, in this direction. And you can observe that voltage across the device is always VBR. And we are talking about negative x-axis. So here V, anode to cathode, will be negative, or voltage between cathode to anode is positive, right? So once it is in breakdown mode in the reverse direction, after breakdown, reverse bias, I will write it as after breakdown, its current will be infinity, so it never stays in the open circuit mode. This was my cathode, this was my anode, right? Current can have any value, but in reverse direction, cathode to anode, and voltage across the diode, anode to cathode voltage is negative because we are in negative axis, or cathode to anode voltage is positive. So you can replace with an ideal voltage source. Its value is equal to same voltage VBR breakdown voltage. Once it breaks down, the voltage across the diode is constant VBR with a cathode positive, anode negative, right? You should remember that cathode is positive, anode is negative. And the region third was not present in our ordinary diode because it never breaks down in the reverse mode. It will stay up to infinite reverse bias voltage ideally. But even though your Zener diode is an ideal one, it breaks down after a voltage in the negative axis. That voltage is called reverse breakdown voltage, VBR. The other name of that voltage is Zener breakdown voltage, VZ. So this is VBR or VZ. Before voltage is said for Zener breakdown. And compared to our ordinary diode, if our ordinary practical diode breaks down when its PIV, peak inverse voltage, exceeds some value, once a normal diode breaks down, that diode cannot be reusable, so it will lose all of its electrical properties. So after breakdown, ideal diode never breaks down in the reverse direction, but in the case of a practical diode, once it breaks down, you cannot use the diode for another time. it completely loses its electrical properties. Whereas your Zener diode, practical Zener diode, will breaks down after some voltage in the reverse direction, but that breakdown mechanism is called Zener breakdown mechanism, and in ordinary diode the mechanism is avalanche breakdown mechanism. So avalanche breakdown mechanism involves collision between atoms and complete damage of the atomic structure, whereas Zener breakdown happening in the lower reverse voltages. This mechanism is visible even in the low reverse bias ranges, whereas your avalanche breakdown mechanism occurs for higher reverse voltages, right? And once the Zener diode breaks down in the reverse mode, the same diode keeps all its electrical properties, and the same diode can be used for second time, right? So there is a basic difference between ordinary diode and Zener diode. Practically both will breaks down in the reverse mode. Once ordinary diode breaks down, cannot be used. It will breaks down once its PIV, peak inverse voltage, exceeds its maximum value, or reverse bias voltage exceeds PIV rating of the diode, and it will lose complete electrical properties. Whereas Zener diode now breaks down, sorry, Zener diode also breaks down, but it will keep its all electrical properties, right? So Zener diode have three regions: forward, short circuit, reverse biased, before breakdown, open circuit because current is zero, open circuit. Third region, reverse biased and breakdown mode, act as a voltage source between its cathode and anode. That breakdown voltage is called VBR or VZ, right? So these things we should keep in mind while analyzing the Zener diode circuit. Practically, the Zener diode current cannot go up to infinity, minus infinity. There will be a maximum limit. We'll call it as IZ max. And ideally, the reverse current is zero when it is reverse mode before breakdown. But practically, to breaks down, there should be a minimum value of reverse current. We'll call it as IZ minimum, right? Ideally, IZ minimum will be zero. Practically, 1 second. Practically, there will be a non-zero current in the reverse direction, and there should be a minimum current in the reverse direction so that the diode can operate in breakdown region. So for breaking down the diode in the reverse direction, we should ensure a minimum reverse current or minimum current in this direction, cathode to anode, and we should ensure a voltage VBR, its reverse voltage should exceed VBR in magnitude, or the reverse voltage should be greater than the reverse breakdown voltage. So VBR or VZ normally expressed as a positive value. Positive value. Right, positive value. Let us say VZ equal to 6 volts or 5 volts, or VBR equal to 6 volts or 5 volts. Even though it is in negative axis, we will specify it with a positive number. So a Zener diode with a VZ of 6 volts will breaks down if and only if its reverse bias voltage exceeds 6 volts, right? And there will be a maximum limit for I setbacks. Beyond that, the diode gets damaged. So actually, the diode is operating in this region. If the Zener diode has a resistance in the reverse breakdown mode, R is present, then voltage between anode and cathode, or cathode and anode with cathode positive in the reverse direction, will depends on the current flowing through the diode in the reverse direction. So reverse current multiplied by RR, so IR multiplied by RR plus VBR or VZ will be a voltage, right? So when RR equal to 0, this voltage VBR is constant. If RR not equal to 0, you will have an increase in reverse voltage as current increases. Because an increase in current will create a drop across RR that will add up with VBR or VZ, so that VKA, voltage between cathode to anode, is the sum of VBR or VZ without RR plus a drop across RR. So you can expect a slope in the reverse breakdown characteristics if the reverse breakdown resistance RR not equal to 0. And the curve goes to the original one if RR equal to 0. Right? So this is a sharp curve. This will depends on the RR value. RR not equal to 0. Right? These are the things required to identify the properties of a Zener diode in diode clipper circuits. Okay. So let us take a simple example in which your Zener diode is placed like this. Simple example. And it is given that Vz of the Zener diode is nothing but 5 volts. And this is R. Let us assume my input is a 10 sine omega t signal. And you are asked to identify the output voltage, V out. And then you are asked to plot the transfer characteristics of the given circuit, as we did earlier in the normal diode clipper circuit. So as we discussed, we have 3 different cases for our Zener diode, and we don't know which mode it is operating. So we will open it. Its anode was connected to 0 volts reference, and cathode was connected to this output node. When diode is open, the right side branch is open. The downward branch is also open because diode is in open condition. There won't be any current flow through R. There won't be any drop. So this potential will be at same as your V in 10 sine omega t. And that 10 sine omega t will be oscillating between plus 10 and minus 10. Plus 10 and minus 10. So while plotting the output, we should replace the diode with a proper equivalent circuit. For that, we should understand the status of the diode. At present, if you are opening the diode, the potential here is 10 sine omega t. If 10 sine omega t is positive, the diode is reverse biased. If 10 sin omega t is negative, the diode is forward biased. So when 10 sin omega t is negative, we are sure that diode is forward biased because this is at 0 volts. This potential will be negative cathode, anode is more positive than cathode, diode is forward biased, act as a short circuit. The moment it is acting as a short circuit, output will be 0 because nothing is visible at the output, act as a short circuit, Vout equal to 0. All negative cycles, Vout will be equal to 0. Why it is 0? It is acting as a forward biased short circuit switch, ideal closed switch. So Vout equal to 0. Right? And since input is negative, there will be current from 0 to negative value in this direction. Its value will be equal to 0 minus 10 sin omega t divided by R. Right. If 10 sin omega t is positive, 10 sin omega t is positive, we'll have two options. One option is the diode will be in reverse mode before breakdown, region number 2, or reverse biased breakdown, region number 3. If it is in region number 2, it acts as an open circuit because current flowing through the diode is 0 amperes. So it is in open circuit. When it is in second mode will happen, the diode was connected like this. When 10 sin omega t value is less than the breakdown voltage, 5 volts, right? When it is open, the voltage is 10 sin omega t. If that value is less than, the breakdown voltage is given as 5 volts. If that is less than 5 volts, Vin is less than 5 volts, negative, here in this axis. But we have placed a diode with cathode up, anode down. So a positive signal will reverse biases the diode, plus 10 sin omega t. If that reverse bias exceeds 5 volts, so I'm marking the level 5 here, exceeds the 5 volts, it will be in breakdown mode. So before that, if Vin is less than positive 5 volts and greater than 0, that is in this region, red color region, input is less than 5, so diode is about to break down, but it is in stage 2 before breakdown condition. When it is before breakdown condition, it acts as an open circuit. When it is in open circuit, you can see that if this is in open circuit mode, you can see that again there is no drop across resistance R. As we discussed earlier, no drop across R implies Vout is same as the input voltage. Right? Vout is same as Vin in this region. Okay? So it will have a same shape. So input is rising from 0 to 5. Here it is coming down to 5, and this is at 5. This is 0 as we discussed. It is going up to 5, then comes down to 5. And we should know what is happening if Vin goes beyond 5 volts. If Vin goes beyond 5 volts, this voltage will become more than 5 volts. That breaks your diode in the reverse mode with cathode positive, anode negative, 5 volts. So you can replace your diode with a 5 volts source once it is in breakdown mode, third region, right? So once V out is shunted by a 5 volt source, V out will be always 5 volts. So V out remains at 5 volts when input is greater than 5 volts, and this is my 5 volts level. So based on three different modes of operation, region 1, region 2 and region 3. Region 1 output is 0, 0. Region 2 V out equal to V in, same shape. Region 3 in breakdown mode, V out is flat, constant, positive 5 volts. So the waveform will look like the waveform shown here. This is omega t axis, omega t axis. And if it is in breakdown mode, you are applying 10 sin omega t and you are getting only 5 volts here. And the remaining voltage, 10 sin omega t minus 5, 10 sin omega t minus 5 will be dropping across the resistance R in this polarity during this region if V in is greater than 5. And there will be a current in this direction from cathode to anode once it is in breakdown mode, as we discussed in our VI characteristics. The remaining voltage will drop across R. So while coming to the transfer characteristics, once you have the output waveform, you can easily draw the transfer characteristics. First, you should note that your input is varying between -10 to +10 because it is a 10 sin omega t signal. When it is negative, V out equal to 0. When V in is negative, V out should be 0 volts. So this will be flat. For different negative values of V in, V out is always 0. When V in is greater than 0 and less than 5, it acts as an open circuit. So V out equal to V in because there is no drop across the resistance. When it is open, V out equal to V in. V out equal to V in curve will look like a linear curve, straight line with slope equal to 1. Slope equal to 1. Once V in crosses 5 volts and can go up to 10 volts in this particular example, V out is clipped, and that level of clipping is nothing but 5 volts. So this circuit actually clips the negative portion of the input waveform plus all the portion with a V in greater than 5. Here slope will be 0. So your Zener diode will be operating in forward biased mode here, reverse before breakdown here, reverse and breakdown mode in the third portion of your transfer characteristics. Input waveform, output waveform, transfer characteristics. In the examination, they will give you the circuit and 4 transfer characteristics. You have to identify the correct one, or the other way. They will give you the transfer characteristics. You should identify correct circuit among the 4 given circuit, or they will give you the circuit with input waveform and 4 options as output waveforms. You have to identify the output waveform, right? So input output waveforms, transfer characteristics, and analyze of the circuit. We are opening the diode first, then we are identifying the different modes, then we are replacing the diode accordingly, either short, open, or with a voltage source. You should be careful while drawing the voltage source. Cathode is positive, then anode with a VZ value. VZ is the reverse breakdown voltage, VBR or VZ. So this is called a shunt clipper because the diode was present in parallel with output, shunt clipper, and you have two different slopes, S0 here, S0 here, and S equal to 1 in the linear region. All right, let us interchange the position of diode and a resistor. Let me draw my diode like this, and resistance comes across the out. This is V in, as we discussed, 10 sin omega t. And this is my V out. Again, the Zener diode with VZ equal to say 5 volts. This is the resistance R. You are asked to identify the output waveform for a given input waveform. It's a sinusoidal waveform oscillating between plus 10 and minus 10 sin omega. And you have to plot the transfer characteristics also. V out on the y-axis, V in on the x-axis. And the diode appears in series between the input and output, so we'll call it as a series clipper. Right? Again, before analyzing the circuit, we will open the diode. The cathode voltage is nothing but 10 sin omega t, it's clear. Anode voltage is nothing but right side open, left side is also open, no current flow through R, no drop across R. So same 0 volts will be appearing at the anode terminal. So if 10 sin omega t or V in, if 10 sin omega t or V in is less than 0, your diode is forward biased because this is less positive than anode, because anode side is positive 0 volts and cathode is negative. So anode to cathode is positive, diode is forward biased. Act as a short circuit. Right? So when this is acting as a short circuit, V out and V in are same. V out is equal to V in. V out is equal to V in. So in your output curve, if V in is less than 0, that is the case here. Diode is forward biased, acting as a short circuit. V out is same as V in. V in. ഞാൻ audible ആണല്ലോ അല്ലേ? ഒന്ന് chat window പറഞ്ഞു. Okay ആണല്ലോ, ഞാൻ chat window നോക്കില്ല. Right. Okay, thank you. Let us continue. V out equal to V in when V in is less than 0. So my output signal will be same as my input signal when V in is less than 0 or 10 sin omega t is less than 0 or 10 sin omega t is negative. And if my V in sin omega t is positive, of course the diode will be reverse biased. Why it is reverse biased? Anode voltage is 0 volts and cathode voltage is positive sin 10 sin omega t. Talking about positive absolute. There I will have two different cases. Reverse bias before breakdown and reverse bias after breakdown. So the moment 10 sine omega t is less than 5, less than 5, it's my 5 volt level, 5. If it is less than 5, it will be in reverse bias and it is in before breakdown region because you should cross a 5 volts in reverse direction to break the diode in the reverse mode. So before breakdown, so it acts as a open circuit, right? So if 10 sine omega t is greater than 0, right, and less than 5 volts, it is in reverse biased before breakdown mode, act as an open circuit. Once it is open circuit, there is no branch current through R, 0 volts, V out also will be equal to 0 volts. Implies V out equal to 0 volts. So when your input is between 0 to 5 at either ends, 0 to 5, V out is 0, right? V out is 0. When input is in this region greater than 5 and greater than 5, less than 10, it is in reverse bias mode and it breaks down. The diode breaks down, right? Once the diode breaks down, you can replace with diode was connected like this. You can replace your diode with VZ value with the cathode positive, here positive, anode negative. X value will be 5 volts, right? So it acts as an ideal voltage source, ideal voltage source. And what about V out? V in is positive greater than 5. What about V out? V out is nothing but if you are writing Kirchhoff voltage law around the loop, if this signal is a general variable, let us mark it as V in itself, and with the positive negative polarity. So negative positive starting from ground, negative positive plus V out, negative positive plus 5, positive negative minus V in equal to 0. Or V out is nothing but taking V into the right hand side, V in minus 5. It's obvious that negative pole is connected to the output side. So you're subtracting actually 5 volts from the input. And this happens when V in is greater than 5 or V in is positive in this polarity. Right? So you're subtracting 5 volts from 10 sine omega t, right? So V out is nothing but 10 sine omega t was your input minus 5. So if instantaneous value is 5, this value is 5. You are subtracting 5 from 5, you'll get a 0. If you are concentrating on the peak, instantaneous value is plus 10, minus 5, you will get a plus 5, positive 5 peak for the output. If you are subtracting a DC value or adding a DC value from a sinusoidal voltage, the shape of that voltage won't be changing. So it preserves the shape as sinusoidal itself, and peak value is nothing but plus 5. Negative peak is nothing but minus 10 for a 10 sine omega t, right? So in the given circuit, they will ask you to identify the maximum and minimum value of the output voltage. It is clear that V out equal to V in when the diode is forward biased. For that, V in should be negative. V out equal to V in implies negative peak of the input will be the negative peak of the output. That is nothing but minus 10. And positive peak occurs when input is at positive maximum. When input is at positive maximum, here in this example, Zener diode breaks down. We have to subtract 5 volts from the input signal because the diode was connected like this, right? So positive maximum for the input is 10. If you're subtracting 5, 10 minus 5, the positive maximum will be 5. So the circuit will produce a maximum value plus 5 at the output, minimum value minus 10 at the output. Then we have to plot the transfer characteristics. Actually, based on the transfer characteristics, you can easily identify the output waveform and the operation of the circuit or status of your Zener diode. So once your transfer characteristics are ready, everything else can be evaluated, right? So we are varying from input from minus 10 to plus 10. As we discussed, when input is negative, V out is same as my V in, right? V out is same as my V in. So slope will be 1, passes through origin, and input is limited by minus 10 volts. When input is positive, and if that is less than 5 volts, the diode is reverse biased. This becomes open, no connection between input and output. Drop across R will be the output voltage, drop across R will be 0 volts. So output will be 0 when input is between 0 to 5. Clear. When input is greater than 5 volts, you can easily write your V out as input V in minus 5 because Zener diode was connected like this. It is in breakdown mode when V in is greater than 5. Then it is replaced with a positive negative 5 volts. So you have to subtract 5 from V in. And we are talking about positive values of V in. So this is of the form, this equation is of the form y equals mx plus c. Y is my V out on the y axis. V in is my x on the x axis. M is the slope, so slope will be 1 here in this case. Y intercept is c, its value will be at minus 5. So a linear curve straight line passing through 5 and minus 5 with a slope of 1. So it is valid if and only if V in is greater than 5 volts. So the straight line will start from 5 and goes linearly as input goes up. And if you are extending this, it will cross at minus 5. Right? So in this example, you have S equal to 1 region here and here, not equal to 1. And first part of the transfer characteristics passes through origin. Second is a flat with slope equal to 0. Third one is of having a slope 1 and it never passes through origin. It has a y-intercept of minus 1. So transfer characteristics, input and output waveform. If you're connecting your diode the other way, the only thing is that it will be forward biased when input is positive. If you're connecting the diode the other way, input is if input is positive, if you are connecting your diode like this with the resistance here, if your input is positive, diode turns on. So V out is equal to V in for a positive values of V in. Get a curve like this. This is my V out. Then if Vz is nothing but 5, so if it is less than -5, it breaks down. Here it breaks down. And from 0 to -5, it is in reverse mode before breakdown. Current equal to 0. This branch current equal to 0. Diode act as an open circuit. So drop across this resistance will be 0 as we discussed earlier. V out will be 0. 0. And if your V in is less than 5, the reverse bias of the diode exceeds a 5 volts. This is -5. -5 appear here. This is 0 volts. When it is in open condition, it is in 0 volts. 0 volts. It breaks down. Once it breaks down, you should replace the diode with the cathode positive, anode negative. So cathode positive, anode negative, 5 volts. So you're actually adding the 5 volt with the V in, right? V out is nothing but plus minus 5 plus V in. So if you are adding this, Y intercept will be positive 5 and V out is nothing but V in plus 5 if V in is between -10 to -5, right? Because our limit is at -10. So Y equal to mx plus C form, again this mx plus C form. Y intercept is 5. So if you are extending this curve, it will meet at 5 volts Y axis. And slope is anyway 1, m is 1. V out equal to V in, so it passes through -5. And this will be the curve transfer characteristics. Right? Any doubts? ഇത്രയും പറഞ്ഞ കാര്യങ്ങൾ സംശയങ്ങൾ എന്തെങ്കിലും ഉണ്ടോ? ചാറ്റ് വിൻഡോയിൽ പറഞ്ഞ നിങ്ങൾ ഡൗട്ട്സ് ഉണ്ടോ, സംശയങ്ങളുണ്ടോ? ഡൗട്ട്സ് ഉള്ളവർ അൺമ്യൂട്ട് ചെയ്ത് ചോദിച്ചാൽ എന്തെങ്കിലും ഇഷ്യൂസ് ഉണ്ടോ? Zener diode acting as a tripping element in the circuit. Right. Issues ഒന്നുമില്ലാന്ന് കരുതുന്നു. Right. Okay. Now, to understand the properties of Zener diodes better, let us place two Zener diodes like this along with the resistor. Or again, my input is, let us assume 10 sine omega t. And I'm assuming equal breakdown voltages. We said, or I will assign unequal values. We said 1 equal to 5 volt. VZ2 is equal to, let us take 3 volts. This is my diode 1, diode 2. And this is my output voltage. You are asked to identify or plot the transfer characteristics of the given circuit. As I said earlier, once you are clear with the transfer characteristics, you can easily plot the output waveform. And input is varying between +10 and -10. Right? So how to identify the operation of the given circuit. Let us take a case with a positive input first. No problem if you are assigning negative input first, no change at all. But let us go for a positive input signal. When V in, I'm calling it as V in signal. V in is equal to 10 sine omega. V in is equal to 10 sine omega. If V in is positive, greater than 0, what would the conditions of diode D1 and D2? When V in is greater than 0, D1 operating in forward biased mode because its anode voltage is positive and act as a short circuit. Once D1 is forward biased or short, that positive voltage appearing at the cathode of your second diode, cathode positive. Of course, if this branch is open, output is at 0 volts because no drop across R. 0 volts at anode, positive voltage at cathode, D2 will be in reverse biased mode. If that V in is less than 5 volts, V in is less than 5 volts, of course, D2 will be in reverse biased mode, but before breakdown. When V in is between 0 and 5, V in is greater than 0, less than 5, right? So,
5 ಅಲ್ಲಲ್ಲೋ 3 ಅಲ್ಲೇವರ.
All right, sorry, right, 3 volt, correct answer, sorry. We said 2 was, right, sorry. We said 2 was 3 volts. Then if V in is greater than 0, right, and less than 3 volts, that is correct, 3 volt. So V in is greater than 0 and less than 3 volts. D1 forward biased, D2 is reverse biased before breakdown. So before breakdown, you should replace your D2 with an open circuit, right? So if your V in is between 0 and 3, 0 and 3 here, positive, D1 is short circuited, D2 is open circuited. So there is no current to the right, no current to the left, no current through R, no drop across R. V out will be 0. So in this region, V out will be 0. Is it clear? D1 forward biased, D2 reverse biased before breakdown, open circuit. So V out is equal to 0. The moment V in crosses 3 volts, D1 remains in forward biased, no change because it was connected like this. Its anode voltage is going up, so it will stay in on state, short circuit, not changed. Whereas the reverse bias of D2 diode now exceeds 3 volts, and that 3 volts is the breakdown voltage required for diode D2. And diode D2 was connected like this. Right. So once Vin crosses 3 volts, Vin is greater than 3 volts. D1 stays in on-state short circuit, whereas your D2 will breaks down with a potential cathode positive, anode negative of 3 volts. So you're actually subtracting 3 volts from 10 sin omega t. Negative positive 3, you're subtracting 3 volts from 10 sin omega t. And our upper limit is 10 volts here. So I'll write 3 to 10. Vn is between 3 to 10. Not change in D1 status, forward biased, but D2 is in reverse breakdown mode, RBB, reverse biased and breakdown. And V out is nothing but V in minus 3. V in minus 3. Here V out was equal to 0. V out was equal to 0. So if V in is greater than 3 and less than 10, V out equal to V in minus 3, Y equal to Mx plus C. So Y intercept is at minus 3, slope is 1, so curve will be like this. Clear? Okay. Let us take the other cycle, negative cycle. My diode was connected like this, this. So here we are about to draw the waveform. So up to 3 volts, V out equal to 0, 0. V out is equal to 0. V out is equal to 0. Right? Up to 3, 0. 0 to 3 volts 0. Another region 0 to 3 it is 0. Right? These two intervals 0, 3 intervals. Right? If it is greater than 3, V out is nothing but V in minus 3. So at 3 volts, 3 minus 3 you will get a 0 here, right? 0 there. And a 0 here because this 3 minus 3 is 0. If you are concentrating on the peak instantaneous value, 10 volts, 10 minus 3 is nothing but 7. So shape will be sinusoidal with a positive amplitude of 7 volts. Shape will not change, give you sinusoidal shape as such. Right, let us concentrate on negative half cycle. If Vin is negative, if Vin is less than 0, negative, your D1 will be in open condition because its anode is negative. Once this is in open condition, no current through this branch, no current through the output side because output is open. Voltage across R will be 0 because current through R will be 0, implies V out is equal to 0 volts. And that V out equal to 0 volts will continue up to a reverse voltage, a negative voltage, at which the status of first diode changes, D1 changes. And I have connected my D1 like this, anode cathode. If this voltage exceeds or that magnitude exceeds minus 3 volts, sorry, minus 5 volts, 5 is the reverse breakdown voltage. minus 5 volts. And D1 is reverse biased, but that breaks down. That will breaks down. And what about the status of D2? When Vin is negative, this breaks down. Your D2 will be in forward biased condition because D2 was connected like this. Right? So up to 5 minus 5, your D1 is off or open or simply in reverse biased mode. And open implies Vout will be 0. When Vin goes less than minus 5 or exceeds the reverse voltage 5 volts in the negative direction, your VZ1 breaks down and D2 will remains in on state because you are increasing the negative voltage or increasing the value of voltage in the magnitude of voltage in the negative direction. You are actually making this is even very less more negative. So this diode was connected like this, cathode was appearing here, so this will remain in short circuit mode or closed or on state. Here it will be open first, so we got 0 output. Now it will breaks down. Once it is in breakdown mode, your cathode will be positive. You should be take care about this. Cathode will be positive, anode will be negative, and breakdown voltage is nothing but 5. Here actually you are adding a 5 volts with V in to produce a V out. So if V in is less than 0 and greater than minus 5, your D1 is reverse biased, not change for D2, it is in forward biased mode. And we got output as 0. If V in is less than minus 5 and greater than minus 10, the status of D1 will become from reverse bias, reverse breakdown mode. So this is actually reverse before breakdown when V in is greater than minus 5 and less than 0. When it is between minus 10 to minus 5, D1 reverse biased and it is in breakdown mode. So I will write reverse breakdown or BR. Here it is reverse before breakdown. Once it is in breakdown mode, you are replacing with an voltage source with a cathode positive, anode negative. So Vout is nothing but in this case, here it was Vout equal to 0 volts. Last case, Vout is equal to V in plus 5 and you should be take care V in is negative. So y-intercept is plus 5. So this is positive 5. Initially it was minus 3. And slope is nothing but 1 itself. So it will is. So slope is equal to 1. Input is negative, output is also negative. So slope is nothing but equal to 1. So its characteristics will look like a 0 volts here. Input and output increases as input crosses minus 5 and 3 volts. These two levels are magnitudes are corresponding to breakdown voltages of the respective diodes. Right? So here also we'll have a reverse direction. My level is nothing but 5. So up to 5, it will be 0. 0 here corresponds to this level. And if that value is greater than or less than minus 5 because minus 5 level is this one, minus 5. So this region in between these two lines, I have an input that is less than minus 5, goes up to minus 10. So after that, I will have a 0. After that, it is nothing but V in plus 5. But you should take care that V in is negative. You are adding 5 means your amplitude will get down. So minus 5 plus 5 will be 0. Here also minus 5 plus 5 will be 0. Here if you are taking a positive peak, sorry, negative peak, minus 10 plus 5 is nothing but minus 5 with that sinusoidal shape. So in this example, output is between plus 7 and minus 5. So maximum value of the output is plus 7 volts, minimum value is minus 5 volts. And output is equal to 0 for a range minus 5 to plus 3. Minus 5 to plus 3. That you can observe here. This is plus 3 and this is minus 5. During the entire range, Vout is 0. So this is the transfer characteristics of the given circuit. It is a series circuit, series clipper circuit. It clips or attenuates the respective amplitudes by 10 to 7 and minus 10 to minus 5. And those portion in between 3 and 5 is clipped off. This portion is clipped off. No voltage is present at the output side between minus 5 to plus 3. All those range of voltages are clipped off or removed at the output side. Right? Is that clear? Any doubts? So let us wind up today's session. We went up to 7:10. Sorry for the delay. Any doubts? സംശയങ്ങൾ ഉണ്ടോ? Doubts എന്തെങ്കിലും ഉണ്ടോ? Right. Ari Krishnandas says no doubt. G no doubt. Minujos clear. Okay. What about others? Angel clear. Suran Raj clear. Ashmi clear. No clear. Adira clear. Okay. Anybody? Anything else to be explained further? So we'll continue from this tomorrow 10 to 12. So we'll have different circuits. We'll bring up multiple diode circuits tomorrow. And if time permits, tomorrow we'll discuss clamper circuits also, right?